This is section 4.6, projections in the Graham-Schmidt process or orthogonalization. So the idea of this section is related to something we've seen before. You want to remember these orthogonal matrices, that is, matrices of this form, that matrices that have this quality that their inverse is just their transpose. Here we're going to study those a little bit more. So this section is going to have a lot to do with orthogonality, we'll see. So let's look at this definition here. A set of vectors in vector space V is called an orthogonal set of vectors if every pair of vectors in the set is orthogonal. And remember, for vectors in Rn, that just means we can take their dot product and we say these vectors are orthogonal if their dot product is 0. So you might be wondering, well, why are we talking about a general vector space if we only know what orthogonality means for vectors in Rn, like this case over here? Well, we'll see how to kind of generalize this idea of orthogonality a little bit later on in the course. But for now, maybe you can just think of that Rn case when we're talking about orthogonal vectors. We'll see it is a more general concept than just than something that just applies to Rn. But for now, we'll go with this sort of idea of the dot product equaling 0 is really a good test for orthogonality. So if every pair of vectors in the set has this dot product of 0, then you say it's an orthogonal set. We say it's an orthonormal set. An orthonormal set, if it's orthogonal, so this requirement up here, and each vector is a unit vector. So each of those vectors is normalized to have a length 1, right? Unit vector just means it has length 1. Right. So let's do a quick example here. Is this set orthonormal? Well, let's give these vectors in this set some labels. I'll call this first one V1, the second one I'll call V2, and the third one I'll call V3. Well, to be orthonormal, we need to show that the dot product of any pair is 0, right? We need to show that every pair of vectors here is orthogonal. Since these are vectors in Rn, that just means that we're testing to see that their dot products are 0. Each pairwise dot product is 0. So that would be orthogonality, just to test those three things, and we need to see that each of their magnitudes is 1 if we want it to be orthonormal. Right? That normal part tells us we better have unit vectors only. So these are the things we need to test. Are they all unit vectors? Are they all mutually orthogonal? So let's start testing this out. V1 dotted with V2. I'll just write that as V1. I'm going to pull that 1 over root 6 scalar out. And in the V2 vector, I'm going to pull out the 1 over root 5 scalar. Make this a little easier to actually compute. So I don't know, I've got this root out front, 1 over root 30. Then from actually dotting the vectors, I get 1 times 0 plus negative 1 times 2 plus 2 times 1. Well, it does look like we get 0 here, which means the dot product is 0. V1 is orthogonal to V2. And now we go down the list and we try to confirm these other ones also hold, but the other pairs are also orthogonal. What about V1 and V3? I'll pull that same trick. I'll pull those scalars that are easy to pull out. I'll bring those out front of the dot product. V3, I'll pull out that 1 over root 30. And I'm just dotting the vectors, keeping that scalar stuff out front. Right, because that scalar multiplied on every component isn't going to affect whether we have 0 or not. So 1 times 5 plus 1 times negative 1 times 1 plus 2 times negative 2. And again, we get 0. So far, we're looking good. We just have to check that V2 and V3, right, I should write my conclusion, V1 and V3 are orthogonal. Now finally the last pair. Use my usual tricks of pulling those scalars out front to make it easier. What do I have left? 0, 2, 1, dotted with 5, 1, negative 2. Let's see what I get here. Zero times 5 is 0. 2 times 1 is 2. 1 times negative 2 is negative 2. It looks like we get 0 yet again, so V2 is orthogonal to V3. Every pair of vectors in our set that we started with up here is orthogonal. V1 and V2, V1 and V3, V3 and V2, right? So this is an orthogonal set. We still have to check that it's orthonormal by checking this last requirement up here, that all the magnitudes of our vectors equal 1. So let's go back up to V1, for example. V1 is this vector up here. Remember, the magnitude is just the root of the sum of the squares of the components of the vector. You think of the magnitude squared as the dot product. So for V1, that looks like, let's remind ourselves, V1 up here. Oops. There it is, okay. V1 up here tells us we need to square these components. Again, maybe it'd be easiest if I thought of this as being 1 over root 6 times the vector 1, negative 1, 2. Because a scalar out front is easy to figure out the magnitude of. It's just the absolute value of the scalar, and then I can work with the magnitude of the vector part. And so we get the magnitude of the vectors, just the root of the sum of the squares. 1 squared, negative 1 squared, 2 squared. Looks like we get 4 plus 1 is root 6. Equals 1. Implies this first vector is a unit vector. And we have to check this for the other two as well, for the V2 up here and the V3. Maybe I'll go through that very quickly right here. You can check my work. For V2, it looks like I get 1 over root 5 times the root of 0 squared plus 2 squared plus 1 squared. That's root 5 over root 5. We get 1. Last time we do this, last vector here, V3, looks like that will give me 1 over root 30. Looking back at my V3 vector, this guy up here, 1 over root 30 times the root of 5 squared plus 1 squared plus 5 squared plus 1 squared plus negative 2 squared. Looks like that is root 30 over root 30. So V3 is also a unit vector. Well, every pair of vectors in this set is orthogonal, right? So the set is orthogonal. Every vector in this set is a unit vector, so this set is orthonormal. Not just orthogonal, but orthonormal. Okay. So let's move on. Let's see this theorem here. Nice fact about these sets we're talking about. An orthogonal set of non-zero vectors is linearly independent. Well, how can we show this? This is not too bad. Let's assume let's say it this way. Let's consider the set of orthogonal vectors, or the orthogonal set of vectors, I should say, non-zero vectors, V1 through Vn. We want to show that since these are orthogonal and non-zero, it must be the case that these are linearly independent. And remember, that means we want to show that if we have a linear combination of these guys, and that linear combination equals the zero vector, implies that all the scalars equals zero, right? That would mean linear independence. Well, so start with this identity that you have a linear combination equal to zero. Let's see if it follows from this assumption that this linear combination equals zero. Let's see if it follows that all those scalars must be zero. So I think we can see this pretty quickly up here. Let me take this equation here that I'm labeling with star, and let me dot V1 on it, on both sides. Well, then on the right side, 0 dotted with 0 is the zero scalar. But notice on the left side, we have C1 times V1 dot V1 plus, we distribute this dot product, right? C2 times V1 dot V2 all the way out to the nth term here. We get this. But notice our set was orthogonal, meaning if I dot any of these vectors in this set with any other one, I get 0. So V1 dot V2, that's 0 here. The next one, all the way through V1 dot Vn, that's a 0. So that implies that only this first term survives, and we get C1 times V1 dot itself equals 0. Right, equals the 0 on the other side of the equation here. But when I dot a vector with itself, I'm really just getting the magnitude squared of that vector. And we know that this V, we know these are non-zero vectors, so this guy's magnitude is not 0. Right, so that means the only way we can satisfy this equation is if C1 is 0. Repeat this process. Instead of dotting with V1, dot with with all the other vectors. So dot with V2 all the way out through Vn separately to similarly show that all scalars, squeezing it in here, C1 through Cn, must equal 0. Right, this same process we did by multiplying in the V1, by dotting in the V1 to both sides of the equation up here. We could do that with any vector, V2, V3, all the way out through Vn, and since all the other terms would fall out, that would leave you just with the coefficient corresponding to the vector you dotted with. Like we got the C1 from dotting with V1. We could get Ci for I equals 1 to n by dotting with Vi. Same process works here. Okay, so let's define a couple more things. I've kind of made a mess here. Let's see if I can separate this out. There we go. Okay, good enough. Let's define something here. Let's look at this definition. A basis consisting of an orthogonal set is called an orthogonal basis. Not a big leap there, just giving an obvious name to something. If a basis is an orthonormal set, so all the vectors are orthogonal to each other and unit length, We call it an orthonormal basis. So you might want to think, can we remember an example of one of these orthonormal bases we've already seen? Yeah, I think you've seen quite a few of these actually. For example, the set 1, 0, 0, 1. It's like our I and j vectors in the plane. That's an orthonormal basis for R2. The I, j, and k vectors, 1, 0, 0, 0, 1, 0, 1, 0, 0, those form an orthonormal basis in R3. Right, these are certainly orthogonal. You can check that they dot to equal 0, and they're each unit length. So that'd be an orthonormal basis for R2. They're a basis, right? So being orthogonal and unit length makes it an orthonormal basis. So an orthonormal basis, why do we care about these things? It turns out they're very nice in a very specific way. I want to see in what way are these orthonormal bases nice. So this is theorem 4.20, your book calls it. Let U1 through UN be an orthonormal basis. So these are all mutually orthogonal and have length 1, unit vectors. So let these be an orthonormal basis for vector space V. Let V be any vector in the vector space. V can be written as a linear combination of these basis vectors very simply in this form, where it's very easy to find how to express it in terms of those basis vectors. Right? It's just that our vector we take is the vector itself dotted with U1 in the U direction, plus the vector itself dotted with U2 in the U2 direction, all the way out to the vector itself dotted with UN in the UN direction. So it's looking like we're just saying that the linear combination of these basis vectors that makes any vector is really easy to find. The scalars you need are just the vector you start with dotted into the vector whose scalar you need. V.U1 is the scalar on U1. V.UN is the scalar on UN. That's an extremely simple formula, so it's something that's very nice about these orthonormal bases. They kind of yield these very easy descriptions. So a little proof here for this is pretty simple. Notice since the U vectors do form a basis of V, and this little vector V is in that vector space V, well, we can write this little v in terms as a linear combination of these basis vectors. That's one of the parts of the definition of a basis. V can be written as a linear combination of these guys. So our goal is really just to show that those scalars that you get are equal to v.u1 attached to the u1 vector, v.u2 attached to the u2 vector, and so on. So what we're saying is we need to show that c1 is v.u1 all the way out through cn is v.un. Well, I think this is pretty easy to do. Let's pick up with our linear combination here. Let me even write out a few more terms of this to be clear. Okay. Now we do the same sort of trick we saw before. We will dot both sides of this with, for example, let's dot it with U1. Then that dot product, again, remember it sort of distributes to each of the terms over here, distributes through the sum. So we get that u1 dot v has to be c1 times u1 dotted with itself. That's this first dot product. I just pulled the scalar c1 out front of it. Plus c2 times u1 dot u2 plus c3 u1 dot u3 all the way out to cn u1.un. But remember, just like we saw in the last little proof, the big thing we want to remember here is that since this is an orthonormal basis, it's orthogonal, every pair of vectors here in this set dots to 0. So if I dot any of those vectors with anything other than itself, I get 0. meaning u1 dotted with u2, that's 0, because those are orthogonal. These guys are 0, because those are orthogonal. Same here, those are orthogonal, because, or the dot product's 0 there, because those are orthogonal. That just leaves u1 dotted with v equals c1 u1 dot u1. Well, remember, u1 is a unit vector, and when I dot a vector with itself, I do just get its length, so that u1 here is just u1 squared in magnitude, but that's 1 since u1's a unit vector. This is an orthonormal basis. So it tells us, oh, forgot my c1 label here. u1 dot v equals c1. And again, so we get exactly what we were looking for. That's not a vector. Let me fix that. We get exactly what we were looking for. This first scalar has to be v dotted with u1. Doesn't matter that I wrote it in the opposite order. u1 dotted with v. Same thing. Well, so all I did here to get this was I dotted this general linear combination of my u vectors that makes v. I dotted it with u1 to get what c1 is. Dot with u2, you'll get what c2 is. Dot with u3, you'll get what c3 is. Dot with un, you would see you do get what we hope it would be. un is v dot un. This holds for every value of I from 1 to n. So this is, I didn't complete the proof here, but maybe it shows you how it works. So let's see this example. Write the vector v equals 1, 2, 3 as a linear combination of the vectors of the orthonormal basis given by u1, u2, and u3, looking like these vectors. These are the vectors we already confirmed do form an orthonormal set, so they are linearly independent by a theorem we saw. There's 3 of them. Well, since the dimension of R3 is 3, and these are 3 linearly independent vectors, we've seen previously that tells us that it does form a basis. If you have as many vectors as the dimension of your space, and they're all independent, they will form a basis of your space. That was one of the things we saw last time. So this is an orthonormal basis. We already proved the set's orthonormal. Now we're saying it's also a basis of R3. Small leap of a conclusion there. Now let's write this vector v as a linear combination. This is going to be super simple. I just want to first label these guys. I'll call the first one u1. Oh, I already have that label. I don't need to do that. I've labeled them that way here. My u1, u2, and u3 equal this set of vectors. So I know how to do this, right? The theorem we just saw said I need to take u1 dotted with v and put that result as the scalar on u1. Plus u2 dotted with v, and I put that result on the u2 vector. Plus u3 dotted with v on the u3 vector. That's all I need to do. So I need 3 dot products. That's really all I have to compute here. Not so bad. Let me compute these down below. u1 equals, u1 dot v equals, u1, I'll pull out that 1 over root 6 factor and dot this with my v vector. What do I get? 1 times 1 is 1, negative 1 times 2 is negative 2, 2 times 3 is 6. It looks like I get 5 over root 6. Look good. What else do I get here? u2 dot v. Again, I'll pull out that scalar 1 over root 5 from the u2 vector, leaving 0, 2, 1, dotted with 1, 2, 3. Looks like this is going to make, we'll go pretty quick through this, 0 plus 4 plus 3 is 7 over root 5. I'm not worried about rationalizing these denominators. That's fine with me to leave those. Finally, u3. So it looks like this one gives us 1 over root 30. All right, so we're almost there. I'd say the last little step is now we know these scalars. Let's go and just write this linear combination out nicely. We are saying that our v vector equals u1.v, which is 5 over root 6. I need that times the vector v, so let's remember the vector v, I'm saying this wrong. I need that dot product times u1. Now let's remember that vector u1 is 1 over root 6, negative 1 over root 6, 2 over root 6. So that's what I'm attaching to this guy. Negative 1 over root 6, negative 1 over root 6, 2 over root 6. Plus u2.v, that's 7 over root 5. That thing needs to be multiplied on the u2 vector, right? The u2 vector is 0, 2 over root 5, 1 over root 5. Oops, this should be a plus. We're adding these up. Plus, finally, u3.v, 1 over root 30, times the u3 vector, which is 1 over root 30, 5 over root 30, 1 over root 30, negative 2 over root 30. That is a linear combination of u1 and u2, u1, u2, and u3 that produces this vector v. Right? This computation is very simple in this way. This is why we like these orthonormal bases. All you have to do is take a dot product to get those scalar values on each of the basis vectors. I should mention here, notice something that simplified our argument up here when we were getting this scalar C1 in our proof was the fact that u1.u1 came out to equal magnitude of u1 squared, which was just 1. That was because this was an orthonormal basis, but for an orthogonal basis, notice you just still have this here, and you could divide it over. So for an orthogonal basis, it's still true that you could figure out these C values are really ui, the ith C value here is ui dot with your vector divided by the dot products of those u's. So you can still easily decompose, find those scalar values, right, that here were the simple dot products. They just look a little more complicated. They are also divided by another dot product, not just the simple dot product up here, but divided by another one if the vectors are only orthogonal but not orthonormal. Orthonormal sure makes this easy. Okay, let's talk about orthogonal matrices a little more. Remember, a matrix A such that A inverse is just its transpose is how we described orthogonal matrices a little while back in lecture. Well, let's start here with this theorem 4.21 that says, let A be a square matrix. The following three statements are equivalent. First, A is orthogonal. B, the columns of A form an orthonormal set. And C, the rows of A form an orthonormal set. So I think this theorem really shows us a little bit more about these orthogonal matrices. This is a very kind of distilled explanation of, or description of these guys, the A inverse is A transpose. But what do we think of these orthogonal matrices? How do we think of these orthogonal matrices? We usually think of them in these terms as well. An orthogonal matrix has columns that form an orthonormal set. Right, think about that. Every column has to be a unit vector, and every column's orthogonal to each other, to every other column. Same for the rows, right? That's a pretty big statement about A. So I want to show just a sketch of the proof here for how this works. Well, I first just want to show that A implies B. Right, that if it's orthogonal, then you get the columns form an orthonormal set. Well, notice if A is orthogonal, we can define this matrix P equals A transpose times A. And by definition of matrix multiplication, that means the ijth term of P is really the ith, I'll say it down here, the ith row of A transpose dotted with the jth column of A. That's what matrix multiplication really does. The ijth element of a matrix product is the ith row of the first one dotted with the jth column of the second matrix in the product. So here I'm thinking of my matrix A is looking like this, having its columns A1, A2, A3, all the way up through AN, the jth one somewhere in here, I'll call AJ. J could be 1 through N, could be any of these numbers. But so I'm thinking of describing A in terms of its columns here, That means A transpose just has the transpose of this vertical column as a horizontal row vector in the first row. It's still the same components as this A1 vector, just made into a horizontal vector. And so on down the transpose matrix. So that makes it easy to see. Ith row of A transpose is just the, really the ith vector, the ith column vector of A just laying on its side. And the jth column of A is just the jth column of A. Well, so I could say when I dot these two, written as a matrix product, it looks like it has all these transposes, but that's really just this vector AI, thinking of it laying down sideways, dotted with this vector AJ, thinking of it as being a vertical vector. Regardless of that, when we dot them, we get the same value, whether we have the transpose or not. So notice here we're saying the ijth element of this P matrix has to be the dot product of the ith row of A. Really, this is really the ith column, right? The ith row of A transpose, the ith column of A dotted with the jth column of A. That's really what this is. But notice, since A transpose is just A inverse, and A inverse times A has to equal the identity, we know this P matrix is just the identity, which implies that the, let's say it this way. Oops. Since we know what the identity looks like, this means that Pij, the ijth element of P, really equals 0 if I isn't J, so we're not in the same row as column. That means we're not in the main diagonal. Or 1 if I equals J, if we are on the main diagonal. Right? We'll just compare these definitions for the ith components of J. Pij is this dot product of the ith column of A with the jth column of A. But Pij is also equal to 1 in this case, where the I and J are unequal, equal to 1 if the I and J are the same. So notice this just implies that the ith column of A dotted with the jth column of A equals this expression for Pij, because it was just another expression for Pij. Oops, this should be equal. Sorry. If they're the same, you get 1. There we go. Right, but notice what this is saying. It's saying if I dot any of these columns with any other column, something in a different column position, I get 0. Meaning every pairwise dot product of these vectors is 0. Meaning every pair of vectors in, every pair of columns in vector A is orthogonal. I'll just use that symbol for orthogonal. And notice if I take I equals to J, notice what this gives me. This becomes just AI dotted with itself, because J is the same as I. But that's just the magnitude of AI squared. And we know that equals 1, because we took the I equal to J case. That means the magnitude of AI is 1. Right, so it's saying each of these for any I, didn't matter which one we took, for any I, we get AI, vector AI, column vector AI is a unit vector. Right. So, what do we have for our result? That means these columns of A form an orthonormal set. They're all mutually orthogonal and they're all unit vectors. So we got that first implication that if A is orthogonal in an orthogonal matrix, then the columns form an orthonormal set. You can prove this part C follows from part A if you just say that which is saying that the rows of A form an orthonormal set if A is orthogonal. To prove that A implies C, just instead of letting P equal A, let's go back up higher, instead of letting P equal A transpose A, let P equal AA transpose. Doing this the same sort of way will let you talk about the rows instead of the columns. Now to show that the same follows in reverse isn't too bad. I think you can probably pick apart most of that proof, but get in touch if you want to talk about that one a little more. This is the big the sort of breakdown I wanted us to see, how we can really say that that orthogonality implies the columns form orthonormal sets and the rows do too. Turns out if you've got these orthonormal sets and your columns are rows, if your rows or columns make up these orthonormal sets, that also means you have an orthogonal matrix. Okay, so let's go on in here to another theorem. If A is an orthogonal matrix, then the determinant of A is positive or negative 1, and A inverse is also orthogonal. So I think the book gives a pretty easy little proof of this, just using some determinant properties here. And let's see, yeah, using a similar little fact here to prove if A is orthogonal, then A inverse is also orthogonal. Well, just remember that A inverse, if A is orthogonal, A inverse is just A transpose. So if I know A being orthogonal implies that the inverse is orthogonal, I can look at A transpose being orthogonal, which remember has the rows / columns of A in its columns and rows, right? They're just interchanged. Columns and rows. So if we knew that A was orthogonal, from up here we know its rows and columns form orthonormal sets. That means A transpose just has these columns and rows reversed, both of which still form orthonormal sets, which imply backwards this equivalence that your transpose is also orthogonal. So it's an easy step from that previous theorem to show this theorem. Now finally, one of the biggest applications here of this sort of orthogonality and dot product business is these vector projections we want to talk about. Vector projections. Now the idea here is given two vectors v and u in Rn with an angle alpha between their tails, so sort of like I've drawn down here, vector u, vector v, angle alpha between their tails. The projection of v onto u, which we usually denote with this notation, PROJ, v onto u this way. The projection vector v onto u is this vector O to A in the picture that I've drawn. So the vector from here to here. And notice this point A that I've stopped at is the point that I would get if I dropped perpendicularly back down from the tip of V to the line containing U. That orthogonality here is important. It makes a right triangle. But wherever that point A lands, the vector from their common tails, V and U's common tail, out to A, that guy is our projection vector. Oops. Is the projection of V onto U. Notice when we're looking at this, you can think of it as the projection of V onto U is just the part of this vector V that's in the direction of U, right? This vector V is up here. If we kind of just think of the shadow coming vertically down, perpendicularly down towards U, the shadow V would cross would be this vector, OA. Right? The shadow that V would cast would be this vector OA here. That's our projection. It's like how much of this vector V is in the direction of U. Notice also from my picture, since from this picture it becomes pretty clear that, well, let's just view it this way. This vector kind of the other leg of this right triangle I've started, this vector here, that is just v minus the projection of v onto u. Right? If I have v along the horizontal down here, u along the horizontal, v up here, notice this little projection vector, this little projection vector down here, if I add it to this guy, I get v back. So all we're really saying is that the projection vector plus v minus the projection vector gives us back the vector itself, right? These cancel, we just get v back. That's all we're saying here. But an important thing to notice is this vector, v minus projection of v onto u, is orthogonal to u. It has to be. It's orthogonal. Sometimes you might hear this called the orthogonal projection of v onto u. Our book doesn't use this notation, but I believe the calculus sequence does. Okay, so we want a formula for this projection vector, and this really isn't so bad. All we need to do is look at this little right triangle I've started up here, right? This right triangle. Notice the magnitude of our projection vector can be found just using trigonometry on this right triangle. It looks like it'll just be the length of the hypotenuse, which is magnitude v, times cosine of this alpha value, of that alpha angle. But now we can remember a couple of things about dot products. Here, if I multiply a magnitude of u into top and bottom, of course that's the same, the u's cancel, I get back where I started. So this is a perfectly reasonable step I took here, but remember there's this theorem about dot products that says the magnitude of two vectors multiplied times the cosine of the angle between them is really just the dot product of your two vectors. Right. This is nice, this is nice. So this is an expression in terms of vectors u and v only. We can figure out an expression for the length of this projection vector. Well then, how do we get the projection vector itself? We just do this. We take the projection vector itself will be whatever length it needs times a unit vector in the direction of this projection. Right, break up the length and the direction separately. We've got all the length taken care of out here. Write down a unit vector in the correct direction of the projection. That won't introduce any more length into the overall result here. It will just give it the correct direction. But the direction of this projection vector is easy, right? It's just the direction of vector u. So the direction of this projection vector is just, let's say it's given by the vector that points in the direction of u, but is a unit vector. So just normalize u. So that's all we need here. We have the right length. All we need to do, right, we have the right length, the magnitude of the projection we already found. Let's just multiply by a unit vector in the correct direction now. There's our length. A unit vector in the correct direction is u divided by its own magnitude. Notice that I can absorb this scalar back with the other scalar. I get u dot v over magnitude u squared u. Make some more space for myself. So finally, we can write it down. The projection of v onto u is really, I'm going to write this scalar stuff as u dot v, just so we can really see what's happening here. Remember, u dot u is magnitude u squared. And we multiply that on vector u. That is a nice formula for the projection. Okay. So now that we've got that formula, we'll copy it down here into the definition I've set up here. The projection of a vector v onto a non-zero vector u in Rn is denoted projection v onto u, the same notation, and is defined by exactly the formula we just saw. By this formula, which maybe we'll write a second time to remind ourselves this denominator is just magnitude of u squared. Okay. Now, so that's if we're projecting a vector onto a vector. Notice if up here I thought not just of u, but of the subspace defined by u. So think of that whole line as being all linear combinations of just this vector u that forms a subspace that looks like a line in Rn. Well, if we project v onto a subspace w generated by u, that line up there, then we call the projected vector projection of v onto w, right? Because we're calling that subspace we're projecting on w. And if that u vector happens to be a unit vector, notice this is factor, this division by u dot u, or magnitude u squared, that's just a factor of 1. So the projection in that case becomes very simple. It's just v dot u multiplied on u. It's okay if I have u dot v instead. That's the same thing, right? Okay, so if we get a unit vector, we saw something about these unit vectors clean these formulas up a lot, like we saw above and as we're seeing here. This formula gets a lot simpler. So let's do a quick easy problem here. Let's determine the projection of 2, 1, negative 1 on 1, negative 1, 3. Easy enough. We're just taking the dot product of our two vectors over the dot product of what we're projecting onto. You can remember what we're projecting onto gets its dot product in the denominator, the v, not the u, not the w. You can remember that's what we are on top of, right? What we're projecting onto. It's in the denominator, so we're on top of it. Erase those nodes there. Okay. So v dot u over u dot u multiplied by u just equals, we'll compute this out. V dot u, that's pretty easy in the numerator. 2 times 1, 1 times negative 1, negative 1 times 3. That's the dot product. U dot u is 1 squared plus negative 1 squared plus 3 squared. Just multiplying this guy with itself, dotting it with itself. And this is all multiplying on vector u. What do we have? 2 plus negative 1 minus 3, that's negative 2. 1 plus 1 plus 9, looks like 11, times this vector. That is it. That's our projection. We could write it all as with that scalar absorbed inside the vector, but this works too. Could write it like that. Doesn't matter which one. So finally, let's see the big result here, what we've kind of been building to, this theorem 4.23, the Graham-Schmidt orthogonalization process. The idea here is, well, if we have a basis, how can we take that and turn it into an orthonormal basis, or derive an orthonormal basis from it? So here's the setup here, and I think we can talk through why this makes sense without actually proving it. Let v1 through vn be a basis for vector space v, or really for a subspace of v would be fine. Right? Subspace is a vector space. So let this set of v vectors be a basis for v. The set of vectors u1 through n, defined as follows, is an orthogonal basis for v. If you want an orthonormal basis, just normalize each of these u vectors, defined the way that we have them down here. So here's the process. To get my first vector in this orthonormal basis, I just take the first vector in my given basis. Right? The v's aren't orthonormal, the u's are. Right? First of all, this is just going to be, let me be clear. Here we are just getting an orthogonal basis of u vectors. If we wanted an orthonormal basis, we'd have to normalize each of these, divide them by their own magnitude. So let's just see how these u's defined this way actually do provide an orthogonal basis without the orthonormal part. So U1, just let it be V. Start in the direction of one of these guys here, say V1. U2, the idea here is U2, you want to take the V1 you've already got, and now you've got some V2 here. Oh, sorry, I want this to be. Right. Notice the V1, that's just your U1. We said that's going to be your U1. So to get another vector, we want to take the projection of this guy onto the direction we've already covered and get rid of that, right? Subtract that out of this V2 vector. Take V2 and get rid of that projection of V2 onto this V1 direction. Right? We don't need that part of it. That part's redundant. We've already covered that part with V1. And we remember, if we subtract the projection of V2 onto something away from V2, we get a perpendicular vector here. So we know this U2 is now perpendicular to V1, which is U1, right? So far, we have enforced that U1 and U2 are perpendicular, yet the two vectors, U1 and U2, span the same space as V1 and V2, right? If you think about this situation embedded in 3D, the plane spanned by V1 and V2 is the same as the plane spanned by U1 and U2. So we haven't lost any generality, we're just figuring out these perpendicular directions in this same plane defined by V1 and V2. Well, so then for vector V3, or for our third vector in our orthogonal basis, we'll take vector V3 and subtract out how much of that is in the U1 and U2 directions already. Right? Just like we took to get V2, U2, we subtracted out of V2 the amount of it that already sat in the direction of U1, covered by the first vector. Right, get rid of all that that's in the direction of this previous vector, you'll have something remaining that's orthogonal to that vector. So we do that for U3, we take the next vector in our given set, subtract out everything that's in the direction of U1, because we already covered U1, and subtract out everything that's in the direction of U2, because we already covered U2 in our basis, and we get something U3 that's perpendicular to both of these. And so you keep up the process until you've gone all the way down and kind of swept this out all the way through them. You just slowly strip off these parts of the new vectors, parts of your old vectors that are in the direction of the new vectors you've already established. That's this process. This is, the way I've described this is far from proof that this set defined this way would be an orthogonal basis for V. But I think it makes sense here. And if you do want more proof, the book goes through it in more detail, and we can certainly talk about it if you contact me. So if I did want to find an orthonormal basis given a non-orthonormal basis, I go through this process, I find my U vectors, and then I just divide them all by their own length. Okay. So why does it work? That's what I was explaining up here. Okay. So let's see this example here. This set 3, 2, 0, 1, 5, negative 1, 5, negative 1, 2 does form a basis in R3. Let's use Graham-Schmidt to find an orthonormal basis for R3 from this given basis. This is not so bad. It says that, let's call our orthogonal basis the set of vectors U1 through U3. Notice we're going to have 3 of these because we know we'll need 3 vectors to make a basis. Since all bases have the same dimension for a given space, and this given basis has dimension 3, we're going to need 3. I think I can not be so lazy here. I guess I can write a U2. That I can do. Okay, so this will be our solution. Call our orthogonal basis that we're trying to craft, call that the set of vectors U1, U2, and U3. U1, we know we just start out by saying is V1. I'll say that's my first vector here, V1. Now U2, remember we said this is going to be our next vector in our set minus the projection Right? Take away the amount of this v2 vector that's in the direction of our first vector, the u1 that we defined. So this is just vector v2, that's not too bad. Vector v2 is 1, 5, negative 1, and we're subtracting the projection of v2 onto u1. Remember that vector's the formula for that is v2 dotted with u1 over magnitude u1 squared times u1. Well, we can compute this since we know v2. v2 is the 1, 5, negative 1 vector, and u1 is this 3, 2, 0 up here. So let's compute this. v2 dot u1, v2 dot u1, let's even write it out and make this as clear as possible. v2 dot u1 divided by magnitude of u1 squared. All times u1. Got some computation to do here, but it's just that, it's just computation. We have 1, 5, negative 1, minus, the dot product gives me 3 plus 10 minus 0. 3 plus 10 is 13. And it looks like the magnitude squared is, oh, this is pretty nice, 9 plus, down here, 3 squared is 9, 2 squared is 4, 9 plus 4 is 13. That's our magnitude squared. Well, this is very nice. Didn't even get anything out of this. This is just 1. We have the vector 1, 5, negative 1, minus 3, 2, 0. Easy to write down. Negative 2, 3, negative 1. That's our u2 vector. Finally, u3 just says go through the same process, but now take v3, the last vector in our set here, in our given basis, 5, negative 1, 2, and subtract off how much of it sits in the direction of the previously established directions. v3 projected onto u1, and subtract off the projection of v3 onto u2. Right? You've already covered those directions. Subtract out how much of v3 is in those directions. You'll get something perpendicular to those directions. So let's write this out. This is v3 is, let me be clear, 5, negative 1, 2. Minus the projection of v3 onto u1, that is v3 dotted with u1 over magnitude u1 squared times u1, minus v3 dotted with u2 for magnitude u2 squared times u2. It's a lot to write down, so let me see if I can do this. 5, negative 1, 2, minus v3 dotted with u1. So v3 is my 5, negative 1, 2. I'm dotting that on u1. Remember u1 way up here, u1 was 3, 2, 0. I'm dividing by the magnitude of that 3, 2, 0 vector, which we already saw. Magnitude squared of that vector, which we already saw is 13. And then I multiply by that u1 vector. Same sort of thing for the u2 now. 5, negative 1, 2 dotted into u2 vector. u2 vector written right above here. Negative 2, 3, negative 1. Divided by size of u2 squared. Looks like 15. Right, just sum of the squares of these components. 4 plus 9 plus 1. And that's all going in the u2 direction. Okay, so now we compute these dot products, see what we have. 5, negative 1, 2 minus, the dot product up here is 15 minus 2, that's nice, that's 13. Working out too nice. Dot product over here is negative 10 minus 3 plus 2, minus 2, that's negative 15. So that turns into a negative 1. What do we have? 5, negative 1, 2, minus 3, 2, 0, minus the negative is positive, plus negative 2, 3, 1. Add it up. 5 minus 3 minus 2 is 0. Negative 1 minus 2 is negative 3, plus 3 is 0. 2 minus 0 minus 1 is 1. Check my work on that. 5 minus 3 minus 2 is 0. Negative 1 minus 2 is negative 3, plus 3 is 0. 2 minus 0 minus 1 is 1. There we go. So now if we want to finish up, right, we have our set of our orthogonal bases. Right, it's this basis U1, which is 3, 2, 0. U2, which is negative 2, 3, negative 1. And finally U3, which is 0, 0, 1. To make this an orthonormal basis, we just normalize each vector, divide it by its own length. The length of this guy looks like it's root of 13. The length of this guy looks like it's root of 14. And the length of this guy is 1. That's nice. So divide that first vector by 13 in every component. The second one by root 14 in every component. And the last one is already a unit vector. I don't need to do anything to that last one. Divide it by 1 if you want, but you don't even have to write that. Here is our orthonormal basis. Now we saw why it's nice to have an orthonormal basis. Every vector in a space has a very easy representation in terms of an orthonormal basis, in terms of linear combinations of the vectors in an orthonormal basis. But it turns out this is a very useful process for coming up with something called the QR factorization, which has lots of applications, including helping you find eigenvalues of a matrix. This is a very important process, this Gram-Schmidt orthogonalization process. Be sure you ask questions if this one's at all unclear. Okay, so that's plenty long for this video, an hour. We'll certainly do it today. More in the next video.